Welcome back. Professor Amos Nevo will continue with his second lecture on intrinsic Diophantine approximation.
Thank you very much, and thank you all for coming to the second talk in this series. So let me start by going very quickly about the plan for today. So last time we talked about density of uniformly discrete point sets. We talked about the discrepancy of dense point sets, and we mentioned equidistribution in the context of discrepancy. We didn't really have much time to talk about equidistribution theorems. Okay, and the plan for today is to talk about approximation exponents on homogeneous spaces, and to give a general geometric lower bound for the approximation exponent, and then to state an upper bound for the approximation exponent, which will be based not on geometric considerations, but on spectral ones. And okay, so that's the plan for today. Let's start by a reformulation of the discussion we had yesterday. So yesterday we considered L, which is a direct product group, G and H non-compact and with an irreducible lattice gamma. We projected gamma to G, obtaining a dense countable subgroup, isomorphic to gamma under our assumptions. And to quantify the density of gamma in G, we introduced the notion of a uniform approximation exponent of a general point, G in G, by elements of the lattice which are of bounded height. And we also introduced the notions of equidistribution and discrepancy associated with the locally finite sets of bounded height elements. That was the content of the discussion yesterday. Of course, this is a complete triviality, but it bears saying. In our case, the space G on which we perform our approximation process can be identified with the homogeneous space L mod H, obviously. And the lattice gamma acts on this homogeneous space of L, as well as on any other homogeneous space of L. And the action in this particular case is the action by left translation on the homogeneous space L mod H, which is G, by a dense subgroup gamma of G. This is a very particular action, the translation action of a dense subgroup on a group. And in particular, this action, we didn't emphasize this yesterday, but we are now, this is an isometric action. Isometric action, these are very, very particular ones. And they have properties which are, you should expect them to have properties much better than a general action. Okay, so we will now generalize this to a considerably or much, much wider class of spaces. We will look at lattice action on homogeneous spaces in general, and not just homogeneous spaces of this form. And so let L be any non-compact, locally compact, second countable unimodular group, not necessarily a direct product. Let gamma be a discrete lattice subgroup of L, and let H be any closed subgroup of L, not necessarily a direct factor. So this is a very general situation. And we assume that every, or at least almost every, gamma orbit in the homogeneous space L mod H is dense. Of course, in the generality in which we work, this is not necessarily the case, but this will be the case in all of the interesting cases, and it's really very, very easy condition to satisfy. For example, the latter holds if gamma acts ergodically on L mod H with respect to the unique L quasi-invariant measure class. And that would always be the case. But notice that we are introducing here some auxiliary information. We have a measure on L mod H, and we also have the notion of ergodicity, and this is necessary in this generality. Previously, when we talked about the isometric case, everything was implied by the denseness of the dense subgroup. Okay, so let the norm of G denote some natural gauge on G, namely a continuous, non-negative, and proper function from L to R plus. This would be essentially a norm, and would be precisely a norm in all the examples we will discuss. Let D denote some natural metric on L mod H, and we would like to analyze the efficiency of approximation by gamma orbits on the homogeneous space L mod H as we did before. We let X be a point in the homogeneous space, and we suppose that for a sufficiently small epsilon, positive epsilon, and for every X naught in L mod H, we can solve the inequality such that the distance between gamma inverse X and X naught is less than epsilon, with gamma in gamma satisfying that the norm of gamma is less than some constant times 1 over epsilon to the zeta, and zeta is some parameter associated with a pair with the orbit and the observation point, which is finite. So therefore, zeta x naught gives a rate of approximation of a general point xf is x naught on the homogeneous space by the gamma orbit of X. And we let kappa x naught be the infimum of admissible rates, zeta. And, okay, so this is our definition of the approximation exponent of the pair. And now, given this setup, it has 3 bits of information in it. The first bit is L, the group underlying our discussion. The second bit is the subgroup H. And the third bit is the lattice gamma. So there's a very wide choice in all 3. And the obvious problems that we would like to consider is, first of all, finiteness. So determine when does there exist a finite constant kappa, depending on L, H, and gamma, which bounds the rate of approximation by almost every lattice orbit. Now, this is a change from what we had yesterday. Yesterday, without saying this explicitly, without making this distinction, we were actually aiming for a much more uniform approximation exponent. In fact, we were aiming for a finite uniform bound for every lattice point without exception. So I'm putting both of these possibilities on the board because the second possibility is, in fact, extremely interesting, and it does occur. And that's what we discussed yesterday. But in this generality, it is absolutely clear that you cannot expect it. And almost sure results are the only ones that will obey such a bound. In other words, if you have a uniform bound, it's going to hold only almost surely and not for every single pair. Okay, so this is an obvious problem, either the almost sure exponent or the uniform exponent. Another thing we would like to do is to give some explicit bounds, which people asked about yesterday. So we want to establish an upper and a lower bound for the rate of approximation and explicate their dependence on L, H, and gamma explicitly. And finally, and this is shooting fairly high, we would like to hopefully or ideally consider the problem of optimality and give a simple and widely applicable criterion for when the upper and the lower bounds coincide. giving rise to the optimal rate of approximation by lattice orbits on the homogeneous space. Okay, so that's what we would like to discuss today with these exponents. And now what I would like to do, I would like to give several more examples beyond those that we discussed yesterday. These examples are going to involve a lot of words with complicated definitions, related to semi-simple algebraic groups over number fields or local fields, etc., etc. But actually, and I'm saying this to those graduate students who haven't mastered the lingo yet, really the examples that we had yesterday, they are very good representatives of at least some of the examples we're going to have here. So if you are not what the definitions here are, these are very good examples to demonstrate them. So one possibility is to take LR to be a real algebraic group defined over Q, and HR an algebraic subgroup, and gamma equals LZ is the lattice of integral points. And that's really already a very rich class of natural Diophantine approximation problems on homogeneous affine varieties, and also actually on homogeneous projective varieties, which we will not discuss today, in these talks at all. Okay. Another possibility is to take, for example, L to be any connected Lie group and H a closed subgroup, and gamma a not necessarily arithmetic lattice subgroup. This includes the example of H being a lattice subgroup itself. So H now is not a connected group or an algebraic group, might be a lattice subgroup itself. So we're looking at one lattice acting by the orbits of one lattice on L modulo another lattice. So it is lattice orbit approximation on locally symmetric spaces. Locally symmetric spaces when L is semi-simple. That's how it's defined. And I should mention that there are many non-arithmetic lattices, although not in every group. And that's a very interesting class. Another possibility, and this is most directly related to what we did yesterday, L is the group of real points, GR times the group of QP points, GQP, of some algebraic group G defined over Q, and H is the QP points. So, okay, this is precisely what we had yesterday. So we are trying approximation in the connected group GR by the dense subgroup GZ 1 over P. And more generally, L is an S algebraic Q group, and H is a closed subgroup, and gamma is the so-called S int, the ring of generated by the inverse of a certain finite collection S of integers. So this setup we will refer to as Diophantine approximation with constrained denominators. Now, constrained denominators is actually a very important approximation problem, and it actually has fairly deep roots, and I'll mention it in a few minutes. There are very, very good grounds to consider constrained denominators. But actually, I mean, if you are interested in classical Diophantine approximation, then okay, what is classical Diophantine approximation? You want to approximate real points by rational points. And typically, nobody tells you that your denominators are constrained. So this is definitely very natural, and so one can also take LA and HA to be groups of rational adels, and gamma equal LQ. So this case, this is just, I don't know, those who are familiar with adels, it's obvious to them, but this is just, it amounts to saying that we are looking at Diophantine approximation by the set of all rational points lying on the algebraic variety, for example, LR modulo HR. So, for example, we can consider approximation by the group of rational points LQ in the group variety LR, or the rational points belonging to a quadratic hypersurface, etc. But this is not, of course, this is not a case where we just look for the most general group on which we can work. The case of approximation by all rational points is very natural. And that's what it involves in our approach. So other natural examples involve algebraic groups over arbitrarily locally compact fields and arbitrary arithmetic and non-arithmetic lattices. And in the present talk, we will focus on explaining a general approach to estimating the approximation exponent kappa LH gamma above and below and give a sufficient condition for optimality. Now, let me give another examples on top of those we saw yesterday, and this would be very relevant to the talk yesterday, not yesterday, the talk on Monday by Professor Dani. So let's consider the affine action on the Euclidean plane. So this is really an extremely elementary case. What you have here is L is the the affine group on the plane. And of course, SL2R is a subgroup. And gamma equal SL2Z semi-direct product Z squared is a lattice. And the homogeneous space, L mod H, is simply the usual Euclidean plane, and gamma acts on it via the usual affine action of the affine group L on the plane. Okay, and so in this case, we have the following proposition. The optimal exponent of approximation for almost every gamma orbit is kappa equals 1. And in fact, and this is, let me state it first and then mention. In fact, more precisely, for every x naught equals the pair u naught v naught in R2, and for almost every x in R2, for every sufficiently small epsilon, it is possible to solve the Diophantine approximation equation gamma inverse x minus x naught in norm less than epsilon, and the norm of gamma is less than b over epsilon log to some power of 1 over epsilon. Okay, so now this I would like to emphasize, and I would like to thank Dmitry Kleinbock for bringing this point up. It is, of course, subject to vigorous objection by people in Diophantine approximation to have an exponent like that, but you have a fuzz which is plus, well, I don't know. In other words, you can only say something intelligent about what happens strictly less than the exponent, or strictly more than the exponent. Now, the situation here is actually much better. We have here the exact exponent, kappa equals 1, and we don't need to add this fuzz. All we have is a certain power of the log. And that is actually very typical in our analysis. In our analysis, in many cases, we can actually come up with a sharp exponent and a certain power of the log. Okay, now, and that is, of course, relevant to some aspects of analogs of Khinchin's theorem that Dmitry Kleinbock mentioned, but I don't think I'm going to focus on this direction in this talk or the next. But I do want to make the point that in the definition of the exponent, there was some infimum over zeta, but actually this result is actually more precise. Yes. Sorry? In principle, yes. Yeah, it does. Now, here is another very important remark. Here you can see that everything is almost sure. And notice that we have left the world of isometric actions. The affine action is as far as you can get from isometric. And in fact, if you compare the expression the norm of gamma inverse x minus x naught and the norm of x minus gamma x naught, they are not comparable at all. And so they're not close, and there is no symmetry between the point x defining the orbit and the point x naught, which we approximate by orbit points. And so our statement, to be precise, is that we say something, okay, what we say is that for almost every orbit, we approximate every point. But this is not a symmetric statement. Okay. This, of course, raises the obvious question of, produce one orbit for which this is actually true. And so this is a very typical problem in Diophantine approximation when you have almost sure results. Okay. Now, just very briefly to mention that results of this type have an obvious implication to, for example, in this case, planar inhomogeneous Diophantine approximation. If we take the resulting two inhomogeneous equations mod 1, namely the equations which are implicit here, then what we're going to get is that for every point on the 2 torus and for almost every point in the 2 torus, for every epsilon sufficiently small, there are integers a, b, c, d, such that these two simultaneous equations are satisfied, such that the determinant of the 2 by 2 matrix is 1, it's in SL2Z, and the maximum, for example, of these integers satisfies the same bound. Yes? Yeah. Yes, it does. Yes, it does. It's not uniform, no. It does. And so here again, the exponent kappa is optimal. Okay, so as I promised yesterday, it's time for us to discuss the literature. I mean, this is not a comprehensive discussion, but a list of a few things which are really extremely relevant. Some previous results in the literature. So we can consider L to be SL2R, age equals N, the upper unipotent subgroup, gamma equals SL2Z, and then the homogeneous space L mod H is simply the punctured plane. And gamma is acting by the usual linear action on the plane. So this is really one of the simplest examples one can think of, very, very basic. And here Loren and Noguera in 2011 established that almost surely the Diophantine exponent is bounded by 3. Just to connect it to the talk on Monday, there is, okay, so if y equals x to the power 3, then x equals y to the 3rd. So the way we write things, everything is inverted. So we have a polynomial bound, and the polynomial bound is 3, 1 over epsilon to the power 3. And their method used continued fraction expansion, which basically means that it's very unlikely to be useful for any other lattice. The optimal almost sure exponent is conjectured to be kappa equals 2 in this case. And Mokorant and Barak-Weiss in 2011 established an explicit but not as sharp almost sure upper bound for arbitrary lattice subgroups of SL2 using results on the effective equidistribution of horocycle flows. And as we saw in Professor Dani's Monday talk, there's been some recent developments in this particular problem, which he gave an exposition for, so I'm not going to try to present any of it. Okay, and so now let's stick still with the linear and affine actions. So for co-compact lattices in SL2C acting linearly on the complex plane, an upper bound follows from an effective equidistribution result of Polycott in 2011. However, for the linear action, establishing the optimal exponent remains an open problem for any lattice subgroup over any field in any dimension. So this is the situation. Now, it is possible to give explicit upper and lower bounds in all of these cases, which was done in this joint work. And so this is really in considerable generality. But these upper and lower bounds do not match, unfortunately. So the optimal exponent remains open. We will have a conjecture for it as things develop. Well, I don't know about the conjecture. We will have a suggestion for it as things develop. Now, for some lattices in SL2C semi-direct C square, whose linear part is a Bianchi group acting affinely on C2, the optimal exponent was established in another joint work. But for every dimension greater than 2, the optimal almost sure exponent for the affine action remains an open problem. So, what I'm going to say is that you can see that optimal exponents, they're not so easy to come by. And so that's why we have, that's why we are promoting our approach to these problems of Diophantine approximation, which uses the tools of spectral theory, because these are so far have been able to give optimal exponents in a fairly large number of cases. Okay, now another very important source of motivation for this whole topic is isometric actions on compact homogeneous spaces. And that is actually a subject which is very deep and it has long roots. So for the sphere S2 viewed as a compact homogeneous space of SO3, an upper bound on the exponent of Diophantine approximation with constrained denominators, and here it was really crucial, for a suitable lattice in the unit group of a quaternion algebra is a consequence of the celebrated Lubotsky-Phillips-Sarnak construction. So they constructed, if you remember, these, well, from these lattices, they constructed actions on the two-sphere with extremely good spectral properties, and these spectral properties they've used for a lot of very, very interesting purposes, and one consequence of their work is that you can derive an exponent of Diophantine approximation for this arithmetic group of units in a quaternion algebra. So this was one of the, definitely one of the first examples of this sort of circle of questions. Very, very successful examples, but okay, I mean, this has really been around for a long time, so I'll not talk about it any further. Now, this approach has been subsequently extended to actions of certain lattices on odd dimensional spheres by Clausel and by O, and more recently in SU2C and SU3C by Sarnak and Parzanchevsky. Okay, so maybe I'll say in just one word that Sarnak, among his really considerable list of talents, is the talent of finding very, very good names for the subjects that interest him. And so this whole sort of theory that he developed recently, he dubbed the theory of golden gates. I'm sure you have, some of you have come across this term. It has a certain reason, but certainly it's a great, catchy phrase. But I can tell you a secret that golden gates really are just a chapter in Diophantine approximation on compact homogeneous spaces. Okay. Now, Duke in 2003 proved an effective equidistribution theorem for the set of all rational points on the sphere. Very beautiful paper. Using estimates of automorphic forms. And this also yields an explicit and effective rate of approximation. And now we come to the subject of this conference, homogeneous dynamics. So the methods of homogeneous dynamics have been applied by Kleinbock and Merrill in 2013, and they have established the best possible exponent for approximation by all rational points. So I'm emphasizing this point on the unit spheres for all n greater or equal to 2. So their result is the best possible exponent, and they have also established a sharp analog of Khinchin's theorem and many other results. So the method of homogeneous dynamics, they have shown to be extremely powerful in this case. Later on, Fishman, Kleinbock, Merrill, and Simmons in 2016 established exponents for approximation by all rational points on homogeneous quadratic varieties, not just on compact ellipsoids. So these varieties, of course, are typically non-compact. And the proof is based on a method of duality in homogeneous dynamics, which was developed by Dani, Margulis, and Kleinbock-Margulis, reducing the problem to analyzing cusp excursions of a suitable abelian diagonalizable group acting on L mod gamma. If you look at this problem, there is no diagonal group and there is no cusps and there is no nothing. So this was judicially chosen to be tailored precisely to this problem on the sphere or on the quadratic variety, and this was very successful. Whether this approach applies to homogeneous spaces beyond quadratic varieties, which could be represented in this way, and also to approximation with constrained denominators, well, that remains to be seen. But in these examples, they were very, very successful. So you can see that exponents are a very rich subject, and there are several competing approaches, which is always a good thing. And we would like to proceed now with explaining our own approach to it. We will be now a little bit more concrete, otherwise the overhead in the notation and definition will be overwhelming. So we will give bounds on approximation exponents on real affine homogeneous varieties. Of course, this is not the general case, but this will give the flavor. So for concreteness, we will demonstrate the main ideas in the following setup. G is a closed, connected, non-compact unimodular subgroup of SLN R. V in Rn is a closed submanifold with G acting transitively on V, so that V can be identified with a homogeneous space G mod H. And we assume that H is unimodular, or equivalently, that V admits a G-invariant infinite Radon measure. And gamma in G is a lattice, which we now assume acts ergodically on G mod H. But this would be very easy to verify in our examples. And we will estimate the almost sure approximation exponent kappa GH gamma for the gamma action on G mod H. And a quick warning, we switch notation here. We had L for a long time, but now we simply look at the triple GH gamma. Okay, so. And we fix a norm on Rn and on M and R, and for x naught in V, we consider the inequality gamma inverse x minus x naught less than epsilon for all epsilon sufficiently small, and with gamma satisfying the norm bound, the norm of gamma is less than b epsilon to the minus zeta for some b. And And this is the third time already, we define the approximation exponent, kappa as the infimum of zeta, such that the foregoing inequality has a solution with the properties stated. And having done that, in the present context, the function kxx naught is in fact gamma times gamma invariant. And hence, it is almost surely a constant. Kappa equals kappa gh gamma, since the gamma action is ergodic. Okay, and so kappa will be called the almost sure approximation exponent, and it does not depend on the norms chosen on Rn and MnR. The invariance is really just a simple consequence of the definition and the usual properties of norms. Sorry? Is there a reason why? Yes, I mean, this doesn't mean anything beyond, it doesn't mean anything beyond the fact that it's constant. Yeah. Okay, yeah. Also, there's also the possibility of infinity, because it may be that you will never find zeta like that. It has to be bigger and bigger. But yes, I mean, to answer your question, it's a constant function, 0, infinity, or a finite constant. Okay, so, so what I'm going to do now, I'm going to try to explain by a heuristic argument. I'm going to derive a lower bound for this approximation exponent. So the most obvious thing that you have to do in order to bound the rate of approximation of a point, observation point x naught in V, it is necessary to estimate how many orbit points gamma inverse x are available for us in a compact neighborhood, small little neighborhood omega of x naught in the space V. That's the most basic question to ask. So let's define the empirical growth parameter for such points. This is a tautological definition. I simply look at the set of all gamma in gamma such that the norm of gamma is less than t and gamma inverse x is in omega. So the points in a large ball in gamma which actually took x into the small neighborhood near x naught. Take the log of this number, divide by log t, take the lim sup as t goes to infinity, and take the sup over all omega compact in V. That's a number. This can always be defined. And the question is, what can we say about this number? Well, how should we think about it? Well, the rate of growth of such orbit points, it actually obeys the bounds satisfied by the volume growth of norm balls, but not norm balls in the underlying group G. It's norm balls in the stability group H. In other words, this parameter A is such that the Haar measure of age t, which is the set of elements in age whose norm is less than t, is comparable to t to the a, where a is greater than 0. And why is that true? This is actually very similar to what we discussed yesterday, and what it's also connected to the notion of a slab that appeared in Jens's talk. So here we have the group G, okay, obviously. And here we have the subgroup H. So the subgroup H is a subvariety. Now, if you're going to take a small neighborhood, let's say x naught is actually the coset of the identity, just to be definite. So a small neighborhood of the identity, well, it amounts to taking a small neighborhood of H. That's the lift of this thing. And so if you want the number of lattice points that takes you into this slab, which projects into the small neighborhood that we have here, it essentially amounts to a version of the lattice point counting problem in this slab. But the growth of this slab, of course, is the volume growth in h, because you're only growing in the h direction. And here, it's a constant. And so if you have a sufficiently robust, sufficiently flexible lattice point counting result, then you are in fact able to count in sets like this, which you intersect with a large norm ball. And if the lattice point counting problem has a positive solution, the number of lattice points is in fact like the volume growth, like the volume of these balls. And so this number A, given a positive solution to the lattice point counting problem in this setup, is comparable to the volume growth in H. Okay, so the number of points available for the approximation obeys that the number of gamma in gamma with norm less than t, and gamma inverse x is in omega is bounded by t to the a. That's the number of points available for the approximation. Now, on the other hand, let's denote by d the dimension of the variety. So clearly, the invariant measure mv on the manifold, it satisfies that the measure of a small ball near v naught, a ball of radius epsilon, is essentially epsilon to the dimension. This is just a completely Euclidean situation, and so this statement is obvious. And therefore, in a compact neighborhood of omega of x naught, there will exist an epsilon separated net, namely a finite set, all of whose mutual distances are at least epsilon, of size at least epsilon to the minus d. And so there are at most t to the a pigeons, namely points of the form gamma inverse x in omega with norm less than t, and at least epsilon to the d pigeonholes, namely disjoint epsilon balls in omega. And so therefore, if the approximation process by orbit points in omega was successful, then we should expect that there are at least as many pigeons as there are pigeonholes. And that implies that t to the a is greater or equal than epsilon to the minus d. And so t is at least 1 over epsilon to the d over a. And so we come here to the following result. Putting in the arguments necessary to make these heuristic arguments precise, we conclude that d over a is a lower bound on the almost sure approximation exponent kappa. It is impossible to approximate almost every point on V as above by points in lattice orbits any faster, namely using matrices of a smaller norm. Okay, and so this is very concrete. D is just the dimension of the homogeneous space, and A is the rate of volume growth with respect to the norm which underlies this approximation process. And now one can suggest a conjecture for the bold, namely that the pigeonhole a priori lower bound is in fact the optimal almost sure exponent always. What we've done here is a very direct, very direct, call it geometric analysis. Obviously, there's no spectrum and there's no spectral theory and there's nothing. And you can, if you have faith, then maybe you believe that the a priori pigeonhole lower bound is always correct. Why not? Okay, so I do not want to state it as a conjecture because I really don't feel that I understand this problem enough to make this conjecture. I mean, it wouldn't, I don't know. It wouldn't be totally surprising to me if there are obstructions that we don't yet see. But I will say that in some situations, we are able to produce the a priori pigeonhole bound. So we know it's optimal. Okay. So now, no. I didn't say it's optimal. I said that if you're very bold, you can conjecture it's optimal. No, but in this case, no, all I'm saying is that it's a lower bound. The theorem once says that it's a lower bound. It doesn't say that it's optimal. That's a good guess. Okay. Okay, so now we want to start our road to deriving an upper bound. Now, the upper bound, according to our approach, but this is not the only approach, and as I said, in work of Kleinbock and collaborators, there were best possible bounds established. So in our approach, we will use completely different considerations, and these will be very briefly spectral estimates in the automorphic representation L to G mod gamma, leading to an effective mean ergodic theorem for age. Now, this is an absolutely crucial point. The point is that in order to understand the gamma action on G mod H, we will need spectral information for age acting on G mod gamma, for age only. Age can be a very small subgroup of G. Okay, this is a crucial point, and it will come back later, but I'm emphasizing it already here. We need spectral information for the action of age only on G mod gamma. And we will use dynamical arguments exploiting the speed of distribution of age orbits in G mod gamma in the form which is sometimes called it's kind of an analog of a shrinking target argument. And we will need an effective duality argument translating a rate in the action of age on G mod gamma to a rate in the action of gamma on G mod H. The rate in the action of age mod gamma meaning what you can derive from the spectral theory of age in L2 G mod gamma. And so here we have, in a very short form, the gist of the idea of the duality principle for homogeneous spaces, which is a very wide-ranging principle which has been around for many decades. But here we would like to give it an effective form. We want to study the action of gamma on G mod age via studying the action of age on G mod gamma. So we begin by considering the intersection of norm balls in G with a stability group H. So HT is the set of age in H whose norm is less than T. The invariant probability measure Y on G mod gamma is denoted mg mod gamma. And we define the averaging operators, pi y beta t. It's an averaging operator from L to G mod gamma to itself. And it's defined precisely in the same way, that we defined it yesterday, except that I switched the left and the right. So pi y beta t f y, okay, we take a point y in the in this probability space. We act by age on the right, and we average on this ball age t, and then we normalize by the measure. Here, of course, this is completely unavoidable, right? Because whenever you talk about duality, you cannot escape the fact that you have two sides. And so, since we've already used G mod gamma, actually, no, sorry, it was exactly the opposite. We had the homogeneous variety G mod H, so we have to put gamma on the left. But of course, it's exactly the same thing. Assume that the effective mean ergodic theorem for the averaging operator holds, namely that there exists a theta such that the average of f on the age orbit, which is what we have here, the average of f on the age orbit minus the space average of f converges to 0 at a rate which is given by a negative power of the volume. For every eta and suitable constant, and for every t greater than t eta. And so this is again exactly what I did yesterday, but I put it here in a somewhat more complicated way because basically theta amounts to the infimum of the rates that we had yesterday. You will see in a minute why I did that. And so I will have just one quick remark because we will get back to the spectral theory. So you may wonder, why should you believe that this will ever happen? Which is a good question. And certainly it does not happen ever when you talk about amenable groups. But that, of course, has to do with the phenomenon of spectral gaps. So actually, this estimate holds in great generality. Indeed, the representation of G in L2 G mod gamma typically has a spectral gap. That's a very well-known fact. In this case, well, okay. And so when it does have a spectral gap, a non-amenable closed subgroup H will typically also have the property that the unitary representation now of age in L2 G mod gamma has a spectral gap as well. And now, for those of you who are familiar with this, I will say something, but I will explain it more tomorrow. So, for example, if age is, for example, a non-compact simple subgroup of G, then the spectral gap for age implies the estimates stated above on the operator norms. So if you actually knew that age was simple and that G mod gamma had a spectral gap, then you will get precisely this estimate for age. Again. Okay. And there are many other cases where such estimates hold, and we will discuss them later. And so now here is our theorem 2, which is an upper bound on the Diophantine exponent. So let G, H, and gamma be as above. So we took a very concrete situation. G is a subgroup of SLN. H is a closed subgroup of G, unimodular, non-compact. G mod H embeds as a variety V inside Rn. We have our norms. We have our approximation process. And assume that age t satisfies the volume growth bound with rate which we denote by A. So the balls, the norm balls in age increase at rate t to the A. And we let D denote simply the dimension of the variety. These are these are the two parameters that went into the lower bound. Okay. Now, assume that the averages beta t supported on age t satisfies the quantitative mean ergodic theorem with rate theta. Then we have the following result. Under the assumption stated above, the Diophantine exponent satisfies the upper bound. Kappa is less than or equal than 1 over 2 theta times d over a, the same d over a that we had before. Namely, it's a multiple of the lower bound by 1 over t theta, by 1 over 2 theta. Now, the most obvious conclusion of this is that if 2 theta equals 1, then the lower and upper bounds for the almost sure approximation exponent coincide. And in that case, we actually have an optimal exponent. And so that puts a lot of focus on this parameter theta. And I can note that 2 theta equals 1 if and only if theta equals 1/2. And yeah, this is the most important part of the talk. And why am I saying this? Because if we go back to the definition, okay, what does it mean that theta equals 1/2? Well, it means that the rate of convergence in the effective ergodic theorem is at a rate which is essentially 1 over the square root of the volume. That is somehow the philosophical meaning of this. You have a rate of decay. I'm not sure I'm able to fully support this statement, but you're going to have here a rate of decay which is the best possible rate of decay, 1 over the square root of the volume. And the conclusion is, if you have the best possible rate of decay of the volume, well, then you're going to have the best possible approximation exponent. Okay, and so these two, well, so best possible rate of decay implies best possible rate of approximation. Okay, so now, okay, I think maybe we'll say 1 or 2 things, but let me just say what's going to happen tomorrow. So I would like to make this much more transparent than it is today, because I only said that there's all sorts of operators and duality, and I'm going to try to make this, well, I mean, it's not going to be fully precise, but I think the heuristics will be quite clear. And then tomorrow also I would like to talk about some other applications of these ergodic theorems in Diophantine approximation. And to the extent that time will allow, we're going to say a few things about spectral theory. So let me just take 1 more minute to say something about spectral theory. Okay, well, I'm just going to finish with these 2 corollaries. So what we said just now is that if the rate of convergence in the mean ergodic theorem for the averaging operators acting on L2 G mod gamma is as fast as the inverse of the square root of the volume of HT, then the rate of Diophantine approximation of gamma orbits on the variety V equals G mod H is best possible. And the Diophantine exponent is given by kappa equals D mod A, a very simple expression, the a priori pigeonhole bound. And specifically, if the stability group H is semi-simple and non-compact, and the restriction of the automorphic representation of G mod gamma to H is a tempered representation of H, then the Diophantine exponent of the irreducible lattice gamma of G in its action on G mod H is best possible. And it is a surprising and useful fact that the foregoing conclusion of subgroup temperedness holds in considerable generality for a large class of triples. And the last thing I'm going to say, I'm going to go way back, and I'm going to go to the examples that we had, or the example that we discussed. So in the affine action, my group L is not semi-simple and it has a unipotent radical, but my group H, in fact, is. It's just SL2. And so since it is, in fact, the case that the action of SL2 on L2 L mod gamma is a tempered representation, so it satisfies the 1 over the square root of the volume estimate, then that is the reason we are and this fact follows from, well, spectral theory associated with SL2, then this is the reason we are able to get the best possible exponent in this case. This is an example of how the system is going to be successful. Okay, thank you very much for your attention.